So now we're going to look at an Enhancement Pmos, and we're going to watch it charging up a capacitor. So in a Pmos, the majority charge carriers are holes, and those are going to travel from a high voltage side to a low voltage side. So that means in this instance here, if we have this transistor and we have a value of 5 volts in this terminal here, and we've got 5 volts on the gate, and the capacitor is originally charged to 0 volts, then we can say here that the charge carrier is going to come from the source, which is a high voltage side here. So this is going to be the source at this side, and this has to be the drain at this side. So again, over here we can put the source and we can put the drain. So the holes are going to come from the positive side down through and charge the capacitor. And this is going to be the actual current flow as well. The conventional current flows in that same direction down through the capacitor. So let's see what's going to happen in this example here. We're going to have the threshold voltage for an enhancement Pmos is -1 volts. So therefore we can say that the VGS, that is the gate to the source, this will be 5 minus the 5 minus the VT. Well, the VT is -1, so it's going to be 5 minus 5 minus -1, which is 0 plus 1, so it's a value of 1. So we've got our VGS minus VT, and we can see here that our VGS minus VT is greater than 0. So if it's greater than 0, then for a Pmos device, this device is cut off. So at the moment this device is cut off, there's no current flowing in it, so it's just a static device with 5 and 5 and 0. Now what we're interested in is that if we were to change the voltage on the gate from 5 volts to 0 volts, then this Pmos device is going to turn on and the current is going to flow into the capacitor here, and it's going to raise the voltage at this point here, and we're interested to find out exactly what voltage this becomes or how far that it gets raised, and also the current types that are going to be flowing. So again, we can write out our equation. We've got our VGS as the gate minus the source, so the gate minus the source is 0 minus the 5, which is -5 volts. And we've got our VGS minus VT, which is -5 minus the -1, which is -4. So VGS minus VT is -4. And now we're interested in comparing that to the VDS. So the VDS is going to be, well, we don't know what's happening at this side here, so we have to try and work that voltage out. So we'll just call that VD. So it's going to be VD minus the VS, which is the value of 5. So VDS is the same as VD minus 5. So let's have a look at this VGS minus VT and we'll compare it. So it's going to be cut off if VGS minus VT is greater than or equal to 0. But VGS minus VT is -4. So -4 is less than 0. So that's not true. So the device is not cut off. So it's never cut off. So now we know the device is not cut off. We know it's taking current. So what type of current is it taking? Or what region is the current in? So it's going to be linear if the VGS minus VT is less than or equal to VDS. So that is -4 is less than or equal to the VDS, which is VD minus 5. So we take this -5 across, it becomes +1. So it's linear if VD is greater than or equal to 1. Now equally we can check for the saturation. It's going to be saturated if VGS minus VT is greater than or equal to VDS, so that's -4 is greater than or equal to VD minus 5. And again, we can transpose this equation, and that's true if VD is less than or equal to the value of 1. So finally we can summarise this by saying that the capacitor here is going to charge in a saturation current up to a value of 1 volt, and then after 1 volt the current is going to be a linear current all the way up to 5 volts. So we're going to get the full 5 volts on this side. So the 5 volts is going to pass all the way through to the drain. So let's have a look at this in the simulator, and again it will become more obvious as to what's happening here. So if you head to the resources section, again you'll find a link and you can open up the simulation file. So in this case here, we're interested in the Pmos enhancement. So it's going to be a threshold voltage of -1. So put that to -1. And we're interested in setting up the gate, source and drain voltages. So we're going to start off with the gate sitting at 5 volts. And we're going to have one side sitting at, our side sitting at 5 volts. This actually will be the source. And we're going to have the drain sitting at 0 volts. So as you can see here, and as was alluded to in the equations, that at these voltages, you can see that the device is cut off. There's no current flowing, and you can see that there's no inversion layer here at all. You see the lines up above the channel. So now what we want to do is we want to now change the gate voltage from 5 volts to 0 volts, and this should turn the device on. So you can see here that's us changed it to 0 volts, and you can see that the device is on. So now we're drawing current through the device, and we're going to be charging up the capacitor. But as the capacitor charges up, it means that the drain voltage here is going to increase. So let's have a look and we'll see what type of current we're going to get flowing. Well, at the moment the drain voltage is at 0 volts, and we can see there's a saturation current. And that's the saturation current you can see here in red, because we've got the pinch off point here. Now if we increase this drain voltage, you can see that as we increase the drain voltage, you can see this line here heading down. So once we get up to 1 volt, you'll see that above 1 volt we then get into the linear region of the current. So it means that between 1 and 4 volts we then have we're in the linear region here for the current, and we could charge that all the way up to 5 volts. So this means with this particular device we're able to pass on the entire 5 volts from this side here over to this side, and it starts off in the saturation current for the first volt, and then for the other 4 volts it's a linear current. So only one more to go, and that'll be us finished with the pass transistors.